This overall section is talking about the derivative and shape of a graph, and this first part of the section is called the first derivative test and test for concavity. Excuse me, and concavity. So the first derivative test, well, let's go through these outcomes first. Explain how the sign of the first derivative affects the shape of a function's graph. State the first derivative test for critical points. Use concavity and inflection points to explain how the sign of the second derivative affects the shape of the function's graph. Explain the concavity test for a function over an open interval. So our first derivative test is something to tell us, it talks about when it's increasing and decreasing of a function. So just recall, if it's a function, if your derivative is positive, it's increasing. If it's negative, it's decreasing. So see how it's decreasing there, decreasing. And so the derivative describes slope, and when the first derivative is talking about the slope of the curve at any given point. So our first derivative test says, suppose that f is a continuous function over the interval I containing the critical point C. If f is differentiable over I, except possibly at point C, then f of C satisfies one of the following descriptions. If f prime changes sign from positive when x is less than C to negative when x is greater than C, then f of C is the local minimum. So in that case, we're talking about, it goes from, change from positive to negative, then it's a local, I should say maximum, I misspoke there. So you get a high point. If, however, it's going to change from negative to positive, you have a local minimum. And if it's the same, on both parts, so either both negative or both positive, then it's going to be neither a local minimum nor maximum, or it could just be a horizontal line as well. So that's these are the points of the first derivative test. So I did want to come back here and talk about this graph a little bit. That just to remind you that this case here on the left, you have a positive slope, then a negative slope. It's going downhill, but the slopes at that point are not the same, therefore it's not, the derivative is not defined. Here you have a negative slope and then a positive slope, so you have a minimum. Here you have a positive slope, then a positive slope, so that doesn't change. So that's not a min or a max. And then you have a positive slope and a negative slope, so that's a maximum. So just to give a nice visual of what this is saying. So problem solving strategies. Using the first derivative test, consider a function f that is continuous over the interval I. Find all critical points f and divide the interval into smaller intervals using the critical points as endpoints. And then you're going to, with those intervals, you're going to find test values. So analyze the sign of f prime in each of the subintervals with test values. If f prime is continuous over the given subinterval, which is typically the case, then the sign of f prime in that subinterval does not change and therefore can be determined by choosing an arbitrary test point x in that subinterval by evaluating it at the sign of f prime at that point. So you're not worried about the value so much as just is it positive or negative. Use the sign analysis to determine whether f is increasing or decreasing over the interval. 3. Use the first derivative test and the results from step 2 to determine whether f has a local max or a local min or neither. So here's our first example. So this first problem says use the first derivative test to find the location of all local extrema for f of x equals x cubed minus 3x squared minus 9x minus 1. And we're talking local extrema, we're not talking, so there's end behavior where it goes up to infinity or down to negative infinity, but we're talking about the behavior towards the middle part of stuff where it gets to high points and low points, but it's not going to be the overall maximum or minimum necessarily. Okay, so for this one, the first thing we're going to do is find the first derivative. F prime of x is going to be 3x squared minus 6x minus 9. And so we can then factor that. I'll just factor a 3 out first. Then we have x squared minus 2x minus 3. And then that would be 3 times x minus 3 times x plus 1. So if we set those equal to 0, x minus 3 equals 0, means x equals 3. And x plus 1 equals 0 means x equals negative 1. So I'm going to slide this over a little bit and use that as other workspace. So our intervals for this are going to be from negative infinity to negative 1, from negative 1 to 3, and from 3 to infinity. And when I make my chart, so I make this chart, you've probably seen the other problems I've done, especially when we're doing rational functions. So it's a similar chart, and there's probably other ways to do this. This is how I like to do this, so feel free to use something else if this is not meaningful for you. So I know that my values, if I don't need this long of lines, let's see here, make those a little bit shorter. Oh, wrong color. Sure doesn't, I'd like to go back to blue. Okay, so boom, boom, boom. And we have negative 1 as a point and 3 as a point. So a value smaller than negative 1 is something like negative 2. And between negative 1 and 3 is 0. And I recommend using 0 when you can. Bigger than 3 would be like 4. So those are test values from those respective intervals. And then I'm just going to put it here 3 times the x minus 3 for one of the factors, x plus 1 for the other. You don't have to do it that way. You could just do the whole polynomial. I think it's easier to do this way, but maybe not. Okay, if I put the negative 2 in here, the result is going to be something negative. With a negative in here, it's negative. So a negative times a negative is a positive. Put the 0 in there, it's negative, and then 0 in the next one is positive. A negative times a positive is a negative. Put the 4 in there, it's positive, and then it's positive, so it's positive. So this means it's increasing here, it's decreasing here, and it's increasing here. So this means that for negative 1, it's going up and then down. So f of negative 1 is a max. And then for the other one, it's going down then up. So f of negative 3 or positive 3 is a minimum. And if you want to get the actual values, I worked it out, but f of negative 1 is positive 4, and f of 3 is negative 28. So you have a local max at negative 1 and 4. You have negative 1, 4, that's the order pair. A local minimum at 3, negative 28. Okay. Let's go on. Here's another one to look at. So we have f of x equals negative x cubed plus 3 halves x squared plus 18x. So our first derivative is going to be negative 3x squared plus 3x plus 18. So if I factor that out, that's going to be f prime of x is going to be negative 3 times x squared minus just an x minus 6. And that's going to be negative 3 times x minus 3 times x plus 2. So we can take these factors, x minus 3 set it equal to 0, get x equals 3, and x plus 2 set it equal to 0, get x equals negative 2. So again, I'll do my chart for this. And again, don't need to draw so long of lines. Here we are. So it was negative 2 and positive 3. So I'll pick some values like negative 3, 0, and 4. Those are my test values. So I'm going to have that. I can't throw away that -3, so I'm going to keep it -3 times x minus 3. Put it with the first one. It doesn't matter which one you put it with. And then just the x plus 2. So -3 times -3 minus 3 is, that's -3 times -6, so positive 18. -3 plus 2 is a negative, so this is a negative. Put a 0 in there. I'm going to get positive for this one, positive here, so it's positive. Put a 4 in there. I'm going to get a negative for the first one because it's 4 minus 3 is 1 times -3 is -3. And then 4 plus 2 is 6, so that's positive. So that's going to give me a negative. So that means it's going down, so it's decreasing, then it's increasing, then it's decreasing. So this means that our min is at f of -2, which is at -22. So at -2, comma, -22. And our local max, I should say local, is at f of 3, which is 40.5. So it's at 3, comma, 40.5. That's it. Okay, let's try another one. Use the first derivative test to find the location of all local extrema. Okay, and use your graphing utility to confirm. So I'll leave that part to you, but I'll do this part. So our f, slide it over so it's not the dead spot, f prime of x is 5/3, that's 5 times 1/3, so 5/3 x to the -2/3 minus 5/3 x to the 2/3. Now, this is a funny one to factor, and so I know that not everyone's comfortable with all their factoring skills, but you would divide out the one with the lowest power, which is x to the -2/3. And we could pull the 5/3 out as well. So this would be 5/3 x to the -2/3, and what's left is a 1 minus, and so the second part, the 5/3 x to the -2/3 divided by 5/3 x to the 5/3 x to the positive 2/3, or 5/3 x to the -2/3 is just going to be an x to the 4/3, because you subtract those powers, 2/3 minus -2/3. So we have 5/3 x to the -2/3 equals 0 when x is 0. Well, I should say x equals 0 is undefined. So that becomes a critical point. And then 1 minus x to the 4/3 equals 0 when x equals 1. I should actually say plus or minus 1. Okay, so we have 3 points here. So I have the -1, the 0, and the 1. So we have 5x to the -2/3. We have 1 minus x to the 4/3. And we'll see what the result is. Okay, so -2 is a good point, -1/2, +1/2, and 2. So putting a -2 in there. So think of that as 5 over x to the 2/3. So that's going to be positive because it squares out the negative. Put the 2 in the next one. So 1 minus 2 to the 4/3, that's negative, so you get a negative. And then put the -1/2 in here. Again, for the first one, it squares down, so that's positive. For the second one, it's a -1/2 to the 4th power, to the 4/3 really. But that's going to make it, the 4th makes it positive, and then, it's going to end up being overall positive. So that's a positive. For the next one, the 1/2, that's going to be positive again, because the next two, in fact, are going to be positive up on top, because there's no way it's going to make it negative. The 1/2 down below is going to be positive still. or the 1/2, and the second one, 1 minus x to the 4/3. So that's positive. And then we have the 2. Now we have 1 minus 2 to the 4/3. Well, that's going to be a negative, so we get a negative there. So what we have is it decreases, then it increases, and then it stays increasing, and then it decreases. So we have for f of -1, which equals 4, or -4, is a local minimum. And then f of 1 is the other one that we have something happening. That's equal to, my battery just died on my pen. Okay, so f of 1 is going to be equal to +4. So that is a local max. And that's it. Okay, let's try another one. So they want us to use the first derivative test to find all local extrema for this next one. And for me, it helps to see this one as an x minus 1 to the 1/3 power. So our derivative, first derivative, is going to be 1/3 times x minus 1 to the -2/3 power, times 1 if you want to follow through with the chain rule. So x minus 1, let's really think of it as x minus 1 to the 2/3 equals 0. And so what we can do from that is cube both sides. So we'd have x minus 1 squared equals 0. And, well, I guess it's just going to be an x minus 1 equals 0, so x equals 1. So we're only 0 here. I was thinking with a squared we have 2, but no, it's on the wrong side. Okay, so we have a 1 here. 0 is smaller, 2 is bigger. So we're looking at 1/3 times x minus 1 to the -2/3. If I put a 0 in there, that's going to be -1, so it's 1 over basically, -1 squared, or -1 to the 2/3, so that's positive. Put a 2 in there, it's going to be 1 over 1 to the 3 times 2/3, if you wanted the whole thing, that's positive. That means it's going up and it's going up. So there's no local extrema. Okay, next one did not print, so I will hand write it in. We have example 5, and it says we have f of x equals -9 times x minus 3 to the 2/3. And it says a is a critical number. And then we have intervals from -infinity up to a, and then from a to infinity. And then we're supposed to find a, and is it a local max or min, or neither? Okay, so if we look at f prime of x, we have -9 times 2/3 times x minus 3 to the -1/3 times 1. So that's going to be, it looks like -6 times x minus 3 to the -1/3. So we have x minus 3 equals 0, so x equals 3. That means our a is 3 here. Now if we set up a table, we have that -6 times x minus 3 to the -1/3. We only have the one critical value of 3, so we can look at 0 and 4. If you put 0 in there, it's x minus 0. Sorry, 0 minus 3. Sorry about that. To the negative 1/3. That's going to still be negative times the negative 6, so it's positive. Put the 4 in there. 4 minus 3 is 1. To the 1/3 is positive, but times negative 6 is negative. So there it is. That means it's going from up to down. So this is a local maximum at f of 3. That's it. Okay. Let's try another one of these that didn't print. So here we have f of x equals negative 2x cubed plus 42x squared minus 240x plus 1. Our f prime of x is negative 6x squared plus 84x minus 240. So it seems really extreme, but you can factor a negative 6 out here, and you end up with x squared minus 14x plus 40 equals 0. Well, you're going to set that equal to 0. So it's negative 6 times, and that could be factored to be x minus 10 times x minus 4 equals 0. So x minus 10 equals 0 means x equals 10. X minus 4 equals 0 means x equals 4. So our intervals are going to be negative infinity to 4, and then from 4 to 10, and then from 10 to infinity. So what do we have here? We have 4 and we have 10. So something smaller is 0, between 5 works, and bigger 11 works. So our factors are x minus 10. I got to remember that negative 6. So I'll put it out front here, negative 6. And then x minus 4. So that's going to be, put a 0 in there, you get a negative times the negative is a positive. Put 0 in here, you're going to get a negative, so the result is negative. Put a 5 in there. 5 minus 10 is negative. Negative 6 times that's still negative. Times negative 6 times it's positive. 5 minus 4 is positive. So you get a positive. And then put the 11 in there. You're going to get a negative and a positive, so it's negative. So our minimum is going to be, so we are going down, then up, and then down. So decreasing, increasing, decreasing. Minimum is at f of 4, which is at negative 415. So the minimum is going to be at 4, comma, negative 415. Our maximum is at f of 10, so we get negative 199. So at 10, comma, negative 199. It's funny thing that 199 would be a local maximum because it's so negative. Okay, and that's it for that problem. So we're going to talk a little bit about concavity and points of inflection. So concavity is, you probably recall the definition of what's concave. Basically, concave down is that, concave up is that. So we're looking for times it's concave up or concave down. And if it's f prime is a decreasing function, well, it's going to depend. If it goes increasing to decreasing, then it's going to be a maximum, or local max, so it's concave up, down. If it's going down, then up, that's a minimum, so it's concave up. So here's our definition. Let f be a function that is differentiable over an open interval I. If f prime is increasing over I, we say f is concave up over I. If f prime is decreasing over I, we say f is concave down over I. So here are some examples. These have positive slopes, so the derivative is positive, so it's concave up. Here's it's decreasing slope, so it's concave down. Here's another increase in slope, so it's getting less negative, so it's still concave up. So if you were to put together this one up here and this one down here, you know, A and C, you're going to end up with a shape like that. But if you put together B and D, so that's increasing, sorry, so it's getting less steep here, and it's getting more steep in the negative direction. So less steep in the positive, more steep in the negative. So it's doing this type of thing, that's concave down. So let's do, test for concavity. This is a cool test. Let f be a function that is twice differentiable, so second derivative over the interval. The f double prime of x is positive. That means the second derivative is positive. That means that it is the change of slope is increasing. So that means you have a positive change of the slope. So a positive change of the slope is a case like this first one. It's getting less negative and more positive. So that's going to be concave up. But if your second derivative is negative, that means the change of slope is getting more, the change is more negative, it's decreasing, then you have concave down. And that's like this case up here where it's getting less positive, less positive, less positive to more negative, more negative, no, more negative. So that's a concave down situation. Another definition, if f is continuous at A and f changes concavity at A, the point A, f of A, is called an inflection point. That's an important thing. That's when the concavity changes. So in a case like this, so you see it's negative, getting less negative, getting now positive. This is concave up. See, the second derivative would be positive because that slope is changing it in the positive direction. And then we see it's positive slope, getting less positive down to zero slope to negative. That is, slope is going down over time. The second derivative is negative, so this is concave down. Now that place where it changes, that's the inflection point. So at the inflection point, and we'll get into this a little more later, but the inflection point, you have the second derivative equals 0, because it's neither increasing nor decreasing. Let me say f double prime at A equals 0. Okay, so for the function f of x equals x cubed minus 6x squared plus 9x plus 30, determine all intervals f where f is concave up and all intervals where f is concave down, and list the inflection points. Okay, so we have our first derivative, f prime of x is 3x squared minus 12x plus 9. And our second derivative is going to be 6x minus 12. So if you take that second derivative, set it equal to 0, you have x equals 2, and that's your inflection point. Okay. So that's where things are changing. So if we look at this in a table, we would have, so 2 is where things change. Testing, testing. I don't see any audio. Testing, testing. Yeah, there we go. Okay. Hope you guys have been hearing me. And I'll choose 0 and 3 as 2 points, test points. We're looking at 6x minus 12. Put a 0 in there, you get a negative. Put 3, you get a positive. So that means it's concave down here. And it's concave up here. So it's concave down from negative infinity to 2. And I hope the wind's not bothering you. Concave up from 2 to infinity. That's funny, the wind just suddenly kicked in. So, sorry about that. If you can tell, I have them next to a stream. It's really pretty here. Thought I'd make some videos outside. Hopefully the sound of the stream is relaxing to you. And there are people playing Alphorn music, which is those big horns, wooden horns, like on the Ricola commercials. Okay, for f of x equals negative x cubed plus 3 halves x squared plus 18x, find all intervals where f is concave up and where f is concave down. It's the same type of thing. We take the first derivative. We're going to get negative 3x squared plus 3x plus 18. And our second derivative is going to give us a negative 6x plus 3. So if we take that negative 6x plus 3, set it equal to 0. So negative 6x equals negative 3, or x equals 1/2. Then we can come up with our chart. So we have the 1/2. 0 is smaller, 1 is bigger. I'll plug in my expressions, negative 6x plus 3, that's that second derivative. If I put a 0 in there, I get a positive. If I put a 1 in there, I get a negative. So that means here it's concave up, and here it's concave down. So concave up is from negative infinity to 1/2, and concave down is from 1/2 to infinity. Okay, there's one last thing I want to share with you is this chart that they have here in the book. What derivatives tell us about graphs? If the first derivative is positive and the second derivative is positive, that means it's increasing and concave up. So here's the case where the first derivative is positive and the second derivative is positive. If the first derivative is positive and the second derivative is negative, so here we have first derivative positive, second derivative negative, and this is considered concave down because it's past this point. That's our inflection point. And then it's on the decreasing of the slope is on the decrease, it's on the decline. Third case, negative first derivative, positive second derivative, that's over here. So it's going down, but it's getting less negative down to this point here where it becomes 0. And then we have the fourth case, the first and second derivative are negative. That means it's decreasing and it's going to be getting more negative. It's getting steeper going in the downward direction. So just to help maybe explain what's going on there. Okay, hope this section gave you some ideas. We will move on to the next part we're going to do is the second derivative test.